Hello again. In this lecture we will discuss the mechanical behavior of materials, and I have three segments. This is the first one where we will talk about things like strength and ductility, cold work, effects on other properties, resilience, and so on. So for this we're going to discuss here. Let me just show you the outline that I have. The outline is shown here that I have. We want to discuss today basically the strength and cold work, and in the next two segments, one segment is going to be on toughness, reliability, and resilience and hardness and impact, and then another final segment will be on fatigue and creep. So let's focus first on what is strength and how do we make materials stronger by imposing cold work, or by using the idea of cold work to strengthen the material. So starting from the basic tensile test, in which we have a load P applied to a specimen. The specimen is usually of standard dimensions, and it has a gauge length. We call it L0 as a gauge length, and it has an initial diameter D0. If it is a round cross section, then the area is A0 is equal to pi D0 to square to the divided by 4. So we have an initial area A0, and we have a load, and therefore initially if the load is divided by the initial cross-section area, we get the stress, which is a uniaxial stress, and we will call it sigma here, in which we will designate it as the engineering stress. So this will be the engineering stress sigma. And as we increase the load, then of course the cross-sectional area is going to decrease. So we would have D0 will continue decreasing, and it will become D, as which is less than D0. So as we increase progressively the stress, the dimensions of the sample will also change. So initial dimensions, if I may just write here, initially we have L0 and we have A0, so this is initial dimensions, and at any current step I have A and L and A, and this will be at any particular load. So the load is, let's say, P, and therefore we can write this as current, or at a particular step I, for example. So we can say Li is the length at step I of loading I, and Ai is the area at that particular loading step. Okay, so based on this, we can derive the stress, engineering stress, as I described it here, P over A0, and we can also find the engineering strain, and the engineering strain is epsilon is equal to delta L divided by L, and delta L is L minus L0 divided by L0, which is right here. So if I divide by L0, then the engineering strain is equal to L divided by L0 minus 1. Therefore, at any current step, I have the condition that at any current step I have epsilon is equal to L over L0 minus 1, which gives me the fact that the ratio of L over L0 is just 1 plus epsilon. So these are initial ideas that we have to construct the engineering, what we call engineering stress strain curve. So let's look at the engineering stress strain curve for ductile materials and for brittle materials. Let's describe it. So if we describe the engineering stress strain curve, on this axis I have the engineering stress that I define sigma. On this axis I have the engineering strain that I define epsilon. And along the way there are specific important points. First, the behavior is going to be linear elastic, all the way linear up to some point in here, some stress and strain. So that point we're going to call it PL. PL is proportional limit. So this is the proportional limit of the material, so the stress is proportional to the strain. It's not yield yet, but it's proportional limit. Beyond the proportional limit, the material can exhibit some nonlinearity. So if you just continue on here, you get a little bit of curvature in the stress strain curve, and we move to another point. The next point is called the EL, and this is elastic limit. And elastic limit, it has some nonlinearity, some curvature, but the definition of the elastic limit is that if you remove the stress or you remove the load, basically, you recover all of the strain. So in other words, up to point EL here, if I remove the load, then the unloading is going to be all the way down to zero. We'll have zero strain at the end of the unloading cycle. Now, if I continue beyond the elastic limit, then I get another point, Y. Y is yield. So PL is proportional limit, EL is elastic limit, and Y is yield. So at this point, if I reach a high enough stress, the material starts to deform plastically, and upon unloading, I do not recover all of the strain that is imposed on the material. I recover only a portion of that. I recover only the elastic part. And then the material goes back to a strain. It will not be strain-free. It will have some amount of permanent deformation that is called residual strain in the material, plastic strain. So if we look here, we see that the unloading from the yield point is going to follow this path. This is a linear path, and we get down to this strain that remains in the material, and this strain, we're going to call it epsilon sub p, and epsilon sub p is a plastic strain. So now one thing that we would notice, that if we continue loading the material beyond the yield point, the material is going to start what we call work hardening. And work hardening is a process by which the material tries to preserve itself by increasing its resistance. And the resistance meaning that you have to really put higher and higher load or higher and higher stress. And that is why you get higher values of the stress, because the material is resisting. And at some point, the resistance of the material ceases to exist, and the load can be decreased, and the material continues to deform. So the maximum point here on the engineering stress strain curve is the ultimate stress, SU. So if we look back here, then SU is now the ultimate stress of the material, or ultimate strength rather than stress. So we use ultimate strength. S is for strength. And the corresponding strain is called epsilon sub u, and epsilon sub u is the ultimate strain of the material. It is not the maximum strain attained, because as the material softens, this is called softening here, softening, because the resistance decreases, we reach a final stress, so S fracture, SF is fracture, strength of the material, so the fracture strength could be smaller than the ultimate strength on an engineering stress strain curve, and the fracture strain is the corresponding value to the fracture strength. Typically for ductile steels, epsilon F could be something like 60%, 50-60%. So the rod, steel rod, ductile steel rod will stretch almost 60% greater length than its original length. That's very, very ductile. If I use another material, for example, cast iron is a brittle material, and therefore it doesn't have this work hardening capacity, and it doesn't have very high ductility. So what happens is that the yield point is reached, and just a little bit beyond the yield, then you reach the ultimate, and therefore for a material that is brittle, S yield is approximately equal to S ultimate. In other words, S ultimate is just a little bit greater than the yield strength, and the failure strain is fairly small. So epsilon failure for a brittle material may be something like 10% or less, and that is much smaller than what we need for designing with the ductile material. So these are the general characteristics for the engineering stress strain curve, and what we require to understand is that as the material deforms, let's say that the length increased by 60%, the cross-section is going to shrink also by a great amount, and therefore if I consider the current state of the material at each loading step, its length is going to be different, its cross-section is going to be smaller, and therefore the local values or the current values of the stress and the strain would be substantially different from what we measure if we were just use the initial state. And therefore we're going to use sometimes in the design we may use what's called the true stress, true strain curve, which I will describe a little bit later. Continuing on, the initial linear part of the relationship between the stress and strain is called the elastic range, obviously. And for uniaxial tension, we have the stress is equal to one constant times the strain. And this constant is called sometimes an elastic constant, sometimes it's called Young's modulus. And for example, for steel, this Young's modulus is 207 GPa. This is gigapascal, 10 to the 9 Pascal, Newton per meter square. So we have table A5. It has typical values for different materials. The higher the value of E, the stiffer the material. So we could use, it deflects less, as we will see later in design applications. If I have aluminum, the elastic modulus is smaller, and therefore it will deflect more. So beyond that point, I'm going to now see how we would obtain the true stress strain curve, taking into account changes in the geometry of the material. So the engineering stress strain curve has a linear part, a little bit nonlinear, but still elastic, yield point, ultimate point, and then fracture. Typical behavior that's seen. However, if I compute now the true values of the stress and the strain, the true stress I'm going to call it sigma prime to differentiate it from the engineering value, and the true strain I'm going to call it epsilon prime to differentiate it from the engineering values. And the general behavior, the linear part doesn't change, but then once we get into work hardening, because the cross-sectional area usually decreases much faster than the decrease in the load in the softening regime, then we get not only that we get this point, the ultimate, but because of in the softening regime, the load decreases a little bit slower than the decrease in the cross-section, then the effective stress or the true stress continues to increase. So typically, the true stress strain curve continues to increase without a maximum point, as we will see here. So I'm going to now discuss how we would find out the true stress strain curve from the engineering stress strain curve. So if I look at, for example, we defined epsilon as equal to delta L over L, which is L minus L0 divided by L0, and this is 1 minus 1 plus L over L0, and therefore we find that L over L0 is 1 plus epsilon. So that's kind of first relationship that we would need, and we figured that sigma is equal to just P divided by the original area. Now, if you consider true stress and true strain, we will start from what is epsilon prime. Epsilon prime is a true strain that is equal to a summation of all of the delta L over L, because we would just do that incrementally. A little bit strain, stop the test hypothetically in our head, and calculate the strain, and then recalibrate, and then increase a little bit of other increment delta L, and so on. And this process, because it is continuous, instead of a summation, I'm going to write it as an integral of dl over L, and the integral is going to start from the original length of the material to the final length L, and that gives me the natural log of L divided by L0. So I'm going to use this as an equation that I need to describe. Therefore, epsilon prime is equal to natural log. Let me just write it a little bit here, erase this, and write it as now epsilon prime is equal to the natural log of 1 plus epsilon, because we found out that L over L0 is given as 1 plus epsilon here. So this equation that I put together here, given epsilon, I can immediately find epsilon prime. In other words, I could convert the strain, engineering strain, to a true strain via this relationship. Next idea is that I'm going to look at the idea of stress. So the stress is sigma prime. The true stress is equal to the load divided by the current area. The current area, I'm going to call it A. And therefore, I can write it P divided by A0 times A0 divided by A. And one idea that we use an approximation is that when the material deforms plastically, the magnitude of the deformation is very large. The plastic part is very large compared to elastic deformation. So for that reason, because the deformation is plastic, is dominated by shear, is based by shear, shear does not change the volume of the material. However, elastic deformation changes the volume material. We know that each material has compressibility, so the compressibility determines how much the material shrinks if you push it hard, and if you let go, then it will rebound back, but there is a small change. So if I compare the elastic deformation to the plastic will be overwhelming, and therefore approximately I'm going to assume that the volume is conserved. The volume does not change because it's dominated by plastic deformation. So A0, L0 is approximately equal to A times L. And this assumption here allows me to write the equation that you see here as L divided by L0. So sigma prime is equal to sigma, because P over A0 is sigma, and L over L0, as we discussed before, is basically, let me write it correctly here. So this will be sigma times L over L0 is 1 plus epsilon. So this is the second equation that I derived today, in which given the engineering values, given sigma and given epsilon, I can make a conversion and find sigma prime and epsilon prime. And that is how I can reconstruct this true stress strain curve from the values of sigma here and epsilon here. These values can be converted to sigma prime and epsilon prime. Now we'll discuss how we would make materials stronger by cold working, the idea of cold work. So idea of cold work is that beyond the yield point, the material deforms a little bit plastically. So if I unload it, it unloads here and I recover the elastic component of the strain. In other words, I recover this component of the strain. So I'm going to divide the strain into a plastic part and an elastic part. The elastic part of the strain is recoverable and is equal to the sigma I is load step I divided by E, the elastic modulus. And the non-recoverable would be epsilon plastic. So if I want to, for example, find the residual strain, and the residual strain may be important in some applications, is epsilon plastic, and this will be epsilon minus sigma I over E. So this is a way for us to compute the residual strain upon unloading. When I have residual strain, we use the term that the material has been cold worked. So we will try to describe cold working, because after removal of the stress, if we just remove the applied load and we have residual strain in the material, and then we try to apply the load one more time. So if we now to apply the load on the upcycle, so if we apply it, the material actually does not yield at the original yield point. It continues to be linearly elastic all the way up to where it came from. And it came from a stress value or a strength value that is sigma I. So it goes back to sigma I, and beyond sigma I, it starts to deform plastically. So the we can consider sigma I now after unloading. We can consider it as a new yield point. So a new yield point after unloading is sigma I, and it is important to describe it. So we're going to describe this with the idea of cold work. The first concept in cold work is to measure the overall ductility of the material. So suppose that I just continue cold working the material until it fails. So the material failed at this point, and I have a strain that is described by the final cross-sectional area A sub F. So the initial area is A0, and then the final area is AF. This is initial, and this is final. So if I plot the load here, P, versus the cross-sectional area, note that the cross-sectional area increases in this direction here. So this is small cross-section here, small, and this is the original here, which is large. However, I have the values. I can measure the cross-sectional area and the corresponding applied load, and therefore I can reconstruct this curve. This curve is important because it can measure the ductility of the material. We're going to define the ductility of the material with an index called the R index, or the reduction area index. And the more reduction area before failure, the more ductile the material is. So R is equal to the original cross-section area minus the final cross-sectional area divided by the original. So we will have 1 minus AF over A0. So this is the case if I push the material all the way to failure. Suppose now we come back to the idea of cold work. How do we define the degree of cold work, and how do we use it to estimate the new value of the yield strength? And is the new value of the yield strength greater than the old value? If yes, then we have achieved hardening of the material, making it harder and stronger. So for the cold work situation here, I'm going to describe it. Let me describe it here as the following. So the cold work is going to be described as, let's say, the degree of cold work. So let's define, let me just choose the different color of the screen. And in this here, white screen. So I have W is cold work index, factor or index, let's say. And W now is similar to R, but when we define R, it's the final state before it fractures. Here we don't want the material to fracture. We're going to push it only to a cross-sectional area that is going to be called AI prime. So AI prime is a load step I that is not causing fracture. So if we look at the previous idea here, here's the idea of cold work. AI prime, let's say we are loaded the material all the way to this point I. So this is step I, you can see high. And it has a load I, and it has a corresponding cross-sectional area A sub I. And then if I unload, the material is going to recover. So the cross-sectional area that was small is going to bounce back a little bit, become bigger. And the bounce back is only elastic bounce. So elastic bounce is this amount here. It looks big on the graph, but it's actually a very small amount. And then the final cross section is AI prime. So AI prime is the final cross section. Because the elastic bounce is not so significant, then we're going to assume that AI prime, for all practical purposes, is approximately equal to AI, here. Therefore, we have W now is equal to A0 over A0 minus AI over A0, and this will be equal to 1 minus AI over A0, and therefore, if I want a relationship between the final value of the cross-section and the initial value, I can write it as 1 minus W. So the W is a fraction, could be 10%, 20%, 30%, but not too large. If I go too large, then the material will fracture. And the cross-sectional area ratio to the original is just 1 minus this fraction. So suppose that the reduction area is described by the cold work factor W is equal to 0.2, then the new area related to the old area is 80%. So basically, I would have to write down that I would have AI prime divided by A0 is 1 minus W. So this will be 80%. Now my objective next is to compute the new yield strength and the new ultimate strength of the material. And we'll do that by considering that we have a relationship between the stress and the strain in the true values. In other words, this should be sigma prime and this should be epsilon prime. This relationship is called the Ramberg-Osgood relationship. And it is similar to Hooke's law, but Hooke's law applies only to the elastic regime. This goes into the plastic regime. And it has two constants. Hooke's law has only one constant, that's E. This has two constants, M and sigma 0. M is approximately equal to the ultimate strain of the material. This relationship is empirical, and we will use it once we know the ultimate strain of the material. Sigma 0 is the strength coefficient. So let's write it down here. If we write down that we have the idea is that we know now sigma prime is equal to, let me just write it down a little bit clearer with the erase all marks. So we can write that sigma prime is equal to sigma 0 epsilon prime to the power m, and m is equal to approximately epsilon ultimate. And therefore, our objective is to compute the new yield point of the material after the cold work. So in other words, I can use this relationship for any value of strain and stress, but I'm interested in the value at which I unload it. So at unloading, I have the strain value that I achieved is equal to the strain value that we obtained from the cold work, which is a natural log of L over L0, and this we wrote it down as the natural log of A0 over A, and A0 is larger than A, so it will be 1 over 1 minus W. So this is, let me just write it down here, as 1 minus W. So we will write it, let me get it back here and start all over again. So here I would write it down as sigma prime equals sigma 0 epsilon prime to the power m, and epsilon prime is equal to natural log of we have L over L0, which is the natural log of A0 over A, which is the natural log of 1 over 1 minus W, and therefore we can find the value of the strain. And we know that M is approximately equal to the ultimate strain of the material, which is a material property. Therefore, the new yield is sigma prime is equal to S yield, this is new, and that is equal to sigma 0, which we know, times now epsilon prime to the power m, so epsilon prime is natural log of 1 over 1 minus W, and this is raised to the power m. So this will be a formula that we could use to find the new yield point of the material. Now I'm going to direct my attention to the next question, which is how do we compute the new ultimate strength, new S ultimate, which is, we call it now S ultimate prime. So the idea here is that at the ultimate point, the ultimate load does not change, whether we are engineering stress strain or the true stress strain is the same. So the idea is that S ultimate times A0 is equal to approximately S ultimate prime times AI, and AI is a step I. And AI is equal to S ultimate prime. This is equal to A0 times 1 minus W. So with that, I have S ultimate prime is equal to S ultimate divided by 1 minus W. So now we have one equation for the new yield, one equation for the ultimate, and it's important to compare them. If the new yield is very close to the ultimate, it means that we harden the material too much and it becoming not as ductile, because it wouldn't have a lot of work hardening capabilities, but it would behave as a brittle material. So too much cold work is not so good. A little bit of cold work may be good because it increases the yield point and the ultimate strength of the material. And with that, we come to the end of this segment on the mechanical behavior of materials, and I'll hope to see you in the next video, and thank you for watching.